Hello people, I'm Bharat Acharya. Welcome to a new video. Today's video, we're going to learn 8051 timer programming. We're going to learn how to produce a delay and what to do with a delay. The most frequently asked program of timers is a typical program to produce a square wave. If you're from Bombay University, you'll see it in probably 7 or 8 out of the last 10 question papers. So it's like almost a short question in the exam. I don't know whether it's going to come or not, but I know that it's very important. It's come a lot. Okay, look here. So here is the question. I'm just telling you the question once. Write a program to generate a square wave of 1 kilohertz. Square wave of 1 kilohertz on a display device connected connected to P1.2, port 1.2. So that's your question. Okay. Now, first let's understand the question. This is 8051. This is port 1.2. That's any port line on which there is a display device connected like a CRO. Everybody knows what's a CRO. You send data, it makes a graph out of that data. So you go on sending 0, 1, 0, 1, 0, 1. It will give you a square wave. So that's your program. Send a 0, send a 1. To send a 0, you need the instruction clear. To send a 1, you need the instruction set P. So clear P1.2, set P P1.2, put it in a loop, you get a square wave. No, it won't be so simple. If it was so simple, then why would it be a 10-mark question? Look here, by just sending zeros and ones, this is what will happen on the screen. This is still a human hand, so there is limitation. When 8051 will do it, it will do it so fast you'll end up seeing a white screen, a white colored screen. That's it. You won't be able to make out the square wave at all. So when something like that happens on a CRO, what do? We slow down the waveform. So over here also we need to slow it down. So we need a delay. When do you need a delay? After sending a 0 or after sending a 1? Both. Different delay or same delay? A same delay will give you a square wave. If you keep different delays, you get rectangular wave. If you keep a delay after 0 but no delay after 1, you'll get a spike kind of waveform. It's called spikes. Anyway, so producing a square wave. Look here, so we need delay, same delay. Now we need to understand how much delay do we want. The question says produce a square wave of 1 kilohertz. Now 1 kilohertz square wave means the time period of the wave will be 1 millisecond. Everybody understands. The inverse of a kilo is a milli. The inverse of a mega is a micro. Giga becomes nano. Tera becomes pico. I'm sure you know that. So 1 kilohertz means 1 millisecond is the whole time period. So if the time period is 1 millisecond, your delay is 0.5 millisecond. Did you understand this? This is the mistake many people make in the exam. They forget to realize this. They just take the delay as 1 millisecond. Square wave is of 1 kilohertz. Time period is 1 millisecond. Your delay is half of that. That is 0.5 millisecond. Let's take one more example. Suppose they say square wave of 2 kilohertz. So if square wave is of 2 kilohertz, time period will be 2 millisecond. Time period will be 1 upon 2, that is 0.5 millisecond. You understand? Time period is 1 upon frequency. 1 upon 1 is 1, 1 upon 2 is not 2, 1 upon 2 is 0.5. Anyway, just joking. So 0.5 milliseconds, that means your delay period will be 0.25 millisecond. I hope you understood this. So whatever the frequency they say, it inverted first of all, that becomes your time period. Half of it is your delay period. So how much delay do we need? 0.5 millisecond. In other words, 500 microseconds. Now who's going to produce this delay? A timer. We have two timers, timer 0 and timer 1. I'm sure you've seen the timer theory video, or you know the theory of the timer if you've not seen the video, either way. So this is your timer. You can use any of the two timers unless they specify in the question which one to use. So I'm using timer 0. Since you want to produce a delay, it will be used as a timer, which means it will clock on the count on the internal clock. The internal clock is of the frequency f oscillator divided by 12. Assuming that frequency to be 12 megahertz. 12 megahertz divided by 12, that means this clock is of 1 megahertz. If this clock is of 1 megahertz, each pulse is a duration of 1 microsecond. Did you understand? If it's counting at a frequency of 1 megahertz, each pulse is a duration of 1 microsecond. If one pulse is a duration of 1 microsecond, counting 500 pulses will give you a delay of 500 microseconds. Please tell me, did you understand this? Let's see. Whatever I said, I'm just writing it on the board. Solution: we use timer 0 as a timer. What is a timer? Internal clock. It counts on internal clock. That means its counting frequency is f oscillator divided by 12. Assuming f oscillator to be 12 megahertz, 12 megahertz divided by 12, counting frequency becomes 1 megahertz. So one count gives you a delay of 1 microsecond. Did you understand this? Now, If you understand this, you understand everything. One count gives you a delay. One count. Each pulse over here is a count. So, one count gives you a delay of 1 microsecond. Required delay is 500 microseconds. That means we must do 500 counts. Did you understand this? So we will tell the timer to do 500 counts. Now if you know the timer theory, to make the timer do 500 counts, you don't load a count of 500 because they are up counters. If you load 500, you come 501, 502, 503, all the way up to 65,535 and then lower flow. So you don't do that. There is a formula. Count to be loaded is max count minus desired count plus 1. Say it again. Max count minus desired count plus 1. So your max count is minus desired count plus 1. Your max count is 65535 minus 500 plus 1. That is 65036. This is your count in decimal. Convert that to hexadecimal FE00. Again, this is a place people make a mistake. This is correct. I'll tell you what mistake people make. People take max count as FFFF. You can. 65535 is FFFF. But if you take FFFF, you can't do minus 500. 500 is a decimal number. FFFF is a hexadecimal number. You're going to get some rubbish count. So either write everything in hexadecimal or write everything in decimal and at the end convert it into hexadecimal. That's what I like to do. So max count is 65535 minus 500 plus 1, that is 65036. Take a calculator, enter 65036, convert to hexadecimal, you will get FE00. Please tell me, do you understand this? Now, this was your count calculation. Now here is your program. Your main program is very simple. As I said, what do we need to do? To produce a square wave, send a 0, send a 1, put it in a loop. So that's what we're going to do. Clear P1.2, that means you're sending a 0. Set B P1.2, that means you're sending a 1. Put this procedure in a loop. After each output, create a delay. And it should be the same delay. The same delay will give you a square wave, a different delay will give you a rectangular wave. So send 0, send 1, put it in a loop. By sending 0, 1, 0, 1 with a delay, you will get a square wave. Tell me, did you understand this much? Now, all we need to understand is how to create a delay. Look here. This is a standard procedure to write a delay routine. Standard procedure is never going to change. Look here. So, this is how you write a delay program. Now this is a standard program, okay? It never changes. Understand this. How to produce a delay has nothing to do with what you want to do after the delay. So, the method to produce a delay never changes no matter what is your question. Do you understand? The method goes like this. First load something in T mod. What does that mean? Choose the mode of the timer. Load the count in TL0, TH0, give your count. Move Tcon, 10, start the timer. I repeat, decide the mode, give the count and start the timer. You don't have to memorize this. Just understand this by logic. What do you want to do first? Do you want to start the timer first? How can you start the timer? If you start the timer and you have not specified the mode, whatever was the previous mode, it will count in that mode. Whatever was the previous count, you do those counts. It won't even accept your new count because it's already started. So that means the first thing you have to do is, starting should be the last thing to do. Before starting the timer, you got to set it up. Do you understand? Now in setup also there are two things to do. Give the mode and give the count. What do you want to do first? The logical thing to do first is give the mode, because in every mode the count changes, the size of the count changes. Mode 0 is 13-bit, mode 1 is 16-bit, mode 2, mode 3 are 8-bit. So why should you give the count and then tell the size of the count? What sense does that make? So the logical approach is first give the mode, choose the mode, so that determines the size of the count, then give the count and then hit the start button or start the timer. Are you clear? Now let's look at these values. Move T mod. I hope you know T mod and Tcon registers. In T mod, these 4 bits are for timer 0, these 4 bits are for timer 1. We are interested in timer 0, so timer 1 bits will be 0. In timer 0, these 2 bits decide the mode. Now timer can work in 4 modes. If you've seen the timer mode theory lecture, the mode to produce a delay, the default mode, the standard mode to produce a delay is mode 1. Every mode is created for a particular reason. Mode 1 is the mode used to produce a delay. So mode 1 means these 2 bits will be 0, 1. You will making it work as a timer. internal clock, that means you're making work as a timer. So this bit will be 0. If this bit becomes 1, that means it works as a counter. Okay, you're making it work as a timer, so this bit should be 0. Gate. Gate is a feature by which you can start and stop the timer using a button using INT0 interrupt. We are doing nothing of that sort. So why keep gate 1? If you keep gate 1, this program will not work. That means you'll have to go to the market, buy a button, buy a wire, connect it to INT0 and press the button. Till the time you don't do all that, the program will not work, and that is not a part of the question. So you're doing something rubbish. So moral of the story, keep gate 0. So that means your whole number formed is 0, 1. I repeat, no need for hardware control, working as a timer. So these two bits are 0 and these two are 0, 1 to indicate mode 1. The remaining bits have nothing to do with our program. Therefore timer 0. So your number is 0, 1H. So the comment I am writing over here is timer 0 is in mode 1. Tell me, did you understand this? Now, you load your count. Your count was FE0C. FE0C means over here you will get 0C, that's the lower byte, and over here you will put FE, that's the higher byte. I'm sure you know this, any number that begins with an alphabet should have a leading 0. So we're putting that 0 just to tell the assembler that it's a number and not the name of a variable, because FE can be the name of a variable and that confuses the assembler. Anyway, so that's why you put a 0. So this is your count. Move tcon, #10. What did I say? What are the steps? Choose the mode, load the count, start. We have chosen the mode, you load the count. We're going to start the timer now. To start the timer, we need the timer run bits. Look here, this is tcon register. These bits are for interrupts, we don't care. These two bits are for timer 1, not a concern. We are working with timer 0, so we are interested in these two bits. What do you want to do? Make the timer overflow or start the timer? Start the timer. So make the run bit 1 and keep the overflow bit 0. Should you keep the overflow bit 1? No, my friend. If you keep the overflow bit 1, then how will you ever come to know when the delay got over? Right now you are starting the timer. Now it has to count up to 500, that is 500 counts, and then will make this overflow 1, indicating that it has overflown. You will keep checking this overflow and wait for it to become 1. If you have already kept it as 1, you will never come to know when it has overflown. Did you understand this? I am telling you, when you finish your job, keep this chalk here. I will keep looking at this in my hand. Whenever the chalk comes here, I know you finish your job. If you keep the chalk here before you started the job or while you were doing the job, how will I come to know when will you finish the job? Because you are supposed to keep this chalk here. That is timer overflow flag. When the timer finishes, it will make overflow flag 1. So you will keep overflow flag 0. Tell me, did you understand this? So keeping overflow flag 0 and run bit 1, this number happens to become 1, the other bits are of no use. So 1, 0H. The comment is start timer 0. Start timer 0. Tell me, did you understand this? Now, timer 0 has started. Like I said, you're going to patiently wait for overflow flag to become 1. The instruction for that is JNB TF0, wait. I hope you understand what does this do in our program. Look here. What did we do in our program? Clear P1.2. So on P1.2 we have sent clear. Clear means we have sent a 0. Now it should not immediately become 1 and again become 0. This 0 should be prolonged. That's what is happening. We are waiting over here for the timer to overflow. When it overflows, we'll come back, send a 1. Then again we will wait for the timer to overflow. When it overflows, we'll come back, send a 0. Again wait for the timer to overflow. That's what this program is doing. I hope you understood the working. Okay, so coming back. JNB TF0, wait. What is JNB? JNB stands for jump if not bit. Say again. Jump if not bit. If TF0, not bit. Not bit means not set. Not set means 0. Let's see how you write. When you write JC, it means jump if carry. So it will jump if carry flag is 1. JNC, jump if no carry, will jump if carry flag is 0. Similarly, JNB, jump if not bit. Not bit means 0. So if TF0 is 0, jump to the location wait. Again, if TF0 is 0, jump to the location wait. TF0 is 0, jump to the location wait. That means this will keep looping over here. This loop will break when this condition is not satisfied, which means when TF0 becomes 1. And if TF0 becomes 1, that means your timer has overflown, because if you know timer theory, when the timer overflows, the first thing it does, it makes the overflow flag 1. Tell me, did you understand this? So wait for timer 0 to overflow. In other words, wait for TF0 to become 1. Tell me, did you understand? Once again. JNB stands for jump if not bit. Not bit means not set. Not set means 0. So if TF0 is 0, jump to the location wait. Again, if it is 0, jump to the location wait. Keep doing this and break the loop when TF0 becomes 1. Tell me, is this clear? So when this loop breaks, the timer has overflown. So what happened? You had chosen the mode, you gave a count, you started the timer, it goes on changing the count. Eventually it has overflown. Job done. You don't go back immediately like a selfish person. My job is done, I go back. No. You're going to clean up the mess you have created. Simple principle in life. After using something, don't spoil it so much that nobody else can use it. Keep it the way it was before you started using it, so that it's equally convenient for everybody. Simple principle applies. Civilized human beings, same thing. Civilized programmers. After you finished your job, clear the bits which became 1 due to your program. The first line, clear TR0. Many people misunderstand this line. What is TR0? Timer run bit. What do you mean by clear TR0? Make the run bit 0. So what does this do? Yeah, exactly. It doesn't stop the timer. If you thought it stops the timer, no, you're wrong. This is mode 1. If you learn timer theory, mode 0, mode 1 and mode 3 are single modes. Only mode 2 is a continuous mode. Only in mode 2 the timer auto starts again. Every other mode, when the timer overflows, it stops. The timer has overflown, so it has stopped. By writing this line, you're not stopping the timer. Then what are you doing? What you're doing is getting the system back into its original state, because right now the system is in a funny state. The timer has stopped, but the run bit is 1. See the irony of the situation. Listen, in the timer theory video, the previous video, I have said this 5 times. If run bit becomes 1, timer starts. If run bit becomes 0, timer stops. Run bit becomes 1, timer starts. Timer stopping doesn't make the run bit 0. Did you understand what I said? The run bit controls the timer. The timer doesn't control the run bit. I never said when the timer stops, the run bit becomes 0. So what has happened? There's a button and there's a fan. The button controls the fan. Button on, fan on. Button off, fan off. Button on, fan on. I hold the fan. The button will not become 0. Button controls the fan. Fan doesn't control the button. The run bit controls the timer. The timer doesn't control the run bit. You made the run bit 1, the timer has started. The timer has overflown and it has stopped. How can the run bit still be 1? The system is in a stupid state right now. The timer has stopped, so the run bit should be 0. It will not automatically become 0. It's your job to make it 0. Tell me, did you understand this? Students say, leave it 1. What difference does it make? Our job is done. Of course, your job is, your fundamental task is over. You produce your delay. But don't be such a silly programmer. What will happen? After you, somebody else will want to use this timer. What will he or she do? They will load the count. The same procedure. Choose the mode, load the count, start the timer. They will start the timer by making the run bit 1. You have already left the run bit 1. If it is already 1 and they will put a 1, that will make no difference to their program. That means the timer will not even start. That means they have written a perfect program, but it will not work because of your mistake. Then they'll come back and see who wrote the program before me, who used this timer. They will look at your program. Imagine what they will tell in their mind about you. I'm just kidding. Understand the point. Don't spoil the system just because your job is done. Clear off everything that you have made 1. You made the run bit 1. It is your job to make the run bit 0, so that the timer comes back to 0 state. Similarly, clear the overflow flag. You made the timer count. The timer counted. It has overflown. When it overflows, it makes the overflow flag 1. You have seen it. Now don't leave it. Make the flag again 0. Again, you're not doing this for yourself. You're doing it for the next programmer. The next programmer, what will they do? Give the mode, load the count, start the timer. Wait for the timer to overflow. How will they wait for the timer to overflow? By checking the overflow flag. If you have already left it 1, they will think that the timer has overflown. They'll be like, how did the time fly so fast? Time has not flown at all. You have written a bad program, and because of that, their program is suffering. So it's your job to clear out the mess that you have created. Things which have become 1 due to your program, which you enjoyed them being 1, now make them 0 and return the system back into its original state, so that the next programmer doesn't have to worry about doing all this. Please tell me, did you understand? You may also argue that, sir, you said in the theory topic that the timer overflow flag is auto cleared. I completely agree. It is auto cleared. When is it auto cleared? When you go to the ISR. Remember that flag becomes 1, we get an interrupt. When we go to the ISR, the flag is auto cleared. Right now we are not going to any ISR. We have not enabled any interrupts. We are not using the interrupt method. So we are not going to the ISR. So the flag will not be auto cleared. It is your responsibility to make this flag 0. That's it. That's your timer program. So once again, let's go through the program. Choose the mode. Always use mode 1 for producing delays. Give the count. Start the timer. Patiently wait for the overflow flag to become 1. That means the delay is over. Job done. make the bits which became 1 due to your program 0. Clear the run bit, clear the overflow flag, and end the program. That's it. So simple. So many times asked question in the exam. Now, what are the changes that can happen? What can they change? Look here. They can change the frequency of the square wave. Like I said, instead of 1 kilohertz, they'll say 2 kilohertz. Time period will be 0.5 millisecond, delay will be 0.25 millisecond. What is 0.25 millisecond? 250 microseconds. That means you do 250 counts. So all that will change is the number that you write over here. Do you understand that? And based on that, this number will change. Based on that, in this program, this number written in yellow color will change. Nothing else will change. Did you understand this? Now, sometimes they do this funny thing. I don't know why. I would want to meet examiners who said that kind of question and ask them, are you really out of your mind that you are asking this? AD51 operates at a frequency of 12 megahertz. We have taken a frequency of 12 megahertz. Why do we take 12? Because when you divide 12 megahertz by 12, you get perfect 1 megahertz, which means every count is a perfect delay of 1 microsecond. That means if you want 672 microseconds, you can get 672 microseconds without any rounding, without any error. That gives you super accurate delays. Now, examiners sometimes use a different frequency. There's a frequency called 11.0592 megahertz, which is also useful. It is useful in serial port programming. The next video will be about serial port. When you learn that, you'll understand there are some standard baud rates. To produce those baud rates, you take a crystal of 11.0592 megahertz. So that is used for serial programming. What they do is, they give a program based on timers, but they take the crystal used for serial port. Why? Just to see whether you can handle. Nobody does it in the real world, but whether you can handle the situation or not, because you are intelligent, so they want to exploit you. So they ask this. Now what happens? If the frequency instead of 12 megahertz is 11.0592, I mean, we can do it mathematically also, but you can also do it orally if you just use your smartness. You're an intelligent person, use your smartness. So they've said frequency of 11.0592. Do you understand? It is less than 12 megahertz. That means it is a lower frequency. That means you are counting slowly, slightly slowly. Now, if you're counting slowly, you can get the same delay in lesser counts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got so much delay in 10 counts. 1, 2, 3, 4, 5. I got the same delay but in half the counts. Why? Because I was counting slowly. Did you understand this much? So, if I want 500 microseconds, and if I was counting at 12 megahertz, I need 500 counts. If I was counting at 6 megahertz, my counting is so slow, I'm taking exactly I'm counting at exactly half the speed. That means exactly half the counts will produce the same delay. Instead of 1, 2, 3, 4, 5, 6, 7, 9, 10, I'm going 1, 2, 3, 4, 5. I got the same delay but in 5 counts. Tell me, did you understand my point? So, if you were counting at 6 megahertz, you would have required 250 counts. But I have not reduced the frequency from 12 megahertz to 6 megahertz. I have got it down from 12 megahertz to 11.0592. That means 11.0592 means basically 11 for the sake of oral calculation. So from 12 megahertz, if we have made it 11 megahertz, that means we've reduced it by 1. 1 in the context of 12 is somewhere around 8%. I'm just giving an oral mental calculation, somewhere around 8%. So we have gone down, we're counting at a frequency 8% lesser. That means the count also approximately should be 8% lesser. So without even having a calculator, because an intelligent person really doesn't need a calculator for everything. If you just use your brains and if you're good with numbers, you can get an oral estimate of course, that the count will be around 460. Okay, that's your oral estimate. Now let's see how far we actually correct. Let's do it mathematically. Come on, look here. Come on, look here. Instead of 12 megahertz, you're counting frequency is 11.0592 megahertz divided by 12. F oscillator divided by 12. This is your counting frequency. If this is your counting frequency, that means one count will give you a delay of exactly the inverse of this. Are you clear? So one count will give you a delay of 12 divided by 11.0592 microseconds. Again, if you were counting at 12 megahertz, you would have got exactly 1 microsecond. One count would have been 1 microsecond. Now one count will be slightly more than 1 microsecond. You don't need to do this calculation. Let this number remain as is. If one count gives you so much delay, X counts will give you a delay of 500 microseconds. We need to calculate X. What is X? 500 divided by this number. 500 divided by 12 multiplied by 11.0592 megahertz. Did you understand this? Take a calculator, do this math. So that turns out to be 460.8. That's our rough estimate was 460 without even touching a calculator. Yes, you don't really need it. But anyway, so it turns out to be 460.8. Now do you understand you cannot do 460.8 counts. You can do either 460 or 461. So what do you have to do? You have to round it. This is exactly the problem of using 11.0592 megahertz. So nobody uses it in the real world. But examiners breed of themselves. They ask such questions which make no practical sense. I mean, come on, ask things that makes a student a better engineer, not a confused person. But anyway, you're not here to argue with them, whatever they want to ask. So if they change the frequency, come on, suppose tomorrow in your paper, some examiner comes up with some weird frequency which doesn't even exist for 8050, and just because that's their person's postal code, who cares? That number will come here. Instead of 11.0592, that is 10 megahertz or 11 megahertz or 12 megahertz, whatever, that number will come here. If it's 12 divided by 12 be exact, so you get 500 counts. Otherwise that number will come here. So that will give you the count. Take this count as 461, then you do 65535 minus this number plus 1 will be your count. Convert that to hexadecimal, that's the count that you will be putting here. So all I said was, in case the frequency is asked is 11.0592, that's the change. Now, suppose they ask you to produce a rectangular wave of 1 kilohertz having 25% duty cycle. 25% duty cycle means on time is 25%, off time is 75%. 1 kilohertz waveform means 1 millisecond is the time period. 25% means 0.25 will be the on time, 0.25 millisecond, and 0.75 millisecond will be the off time. Done. So 0.25 millisecond means 250 microseconds, and this is 750 microseconds. So you'll produce two delays. You'll have two delays, delay 1 and delay 2. One of them will have a count of 65535 minus 250 plus 1. The other will have a count of 65535 minus 750 plus 1. If it's a weird duty cycle, like something like 56% duty cycle. 56% duty cycle means 0.56 and 0.44. Yeah, 0.44. So one will be 65535 minus 560 plus 1, the other one will be 65535 minus 440 plus 1. Basically that's all they can do. Those are things they can change, which again generally they don't change. Generally it's a standard question of square wave 1 kilohertz, but I'm just trying to prepare you for the worst case scenario. I hope you understood how to handle the frequency if it's anything other than 12 megahertz. It's not some rocket science. That will just come over here. That number will just come over here. Everything else will be the same. Okay? All the best.